So this is going to be our practice test number 3. Okay, practice test number 3 is mostly triple integrals. Okay, triple integrals, usual one, this is the way you're going to question. It will give you one ordinary one, straightforward to find. Then there's going to be one that you have to use cylindrical coordinates. There's going to be one that you have to use spherical coordinates. Okay. Then there's going to be one problem on the change of a variable. Okay, and there is going to be a couple of problems that you have to do the volume for us. Just again, you know that the volume by the triple integrals, very similar to the what we are working on. Okay, so starting with the first one. The first one is this is it. I'm going to write it down. It's a triple integral we want to find. So this is going to be the first problem. In the first problem, you want to evaluate this integral. Okay, is a triple integral. It's going to be 1, 2, 3. The function is y squared, and then when you have a dx, a dy, a dz. These are a rectangular type, we call it. And you want to do it over a t, and the t is the region that we're going to integrate, or the solid. In this case, t is a tetrahedron. Is the tetrahedron with the given equation. Okay, tetrahedron in the first okay, in the first octant. So everything is positive, x, y, z. It's going to be in the first octant bonded, as usual, bonded by the coordinate planes, by the coordinates. Okay, coordinate planes means, you know, x0, y0, z0, and the plane with this equation. The equation is going to be 2x plus, you did similar one in the using the double integral. That's the one. Okay, so it's evaluation of a triple integral. So you have to have the range limit of integrations, but the limit of integration is not given to you, but they give it a region. Okay, the solid, if you like. So the solids consist this tetrahedron with this equation. It's just a plane, and then it's going to be the intersection, if you like, with those coordinate planes that we're going to have. Now, what you have to do is we talk about it. You check to see what you have for the z. You need the limits of integration for the z. So check if the equation is given to you in terms of the z. You solve it for z. That your limit for the z. Then you project it into the xy plane. Projected means you replace z by 0. You drop it down. When you drop this one down, 2x plus 3y equal to the 6 can be a straight line. Then this is a straight line and intersection with the x and the y coordinates would make a triangle. Then you decide what, because you know, as soon as you're done with the first part, the second one is a double integral. So this double integral can be, you know, type 1 or type 2. So as soon as you go to the projection, that you will find out and you get the limit of integration and you come back and you do it. Okay, this is the procedure for all of them. So I start with the z. What do you have? You have this equation for the z. So simply solve for z. So that gives it 2x plus 3y plus z equal to the 6. And we solve for z. So that gives us z equal to 6 minus 2x minus 3y. There is no other z. So this z, the limit of the z is the first octant. So z is positive. Okay, then equal to 0 and less than equal to the 6 minus 2x minus 3y. So this is the limit of integration for the z. Any question? Now drop it down into the two-dimensional to go to the, to get the other two. So put z equal to the 0. Z equal to the 0, you end up with a 2x plus 3y equal to 6. So this would be projection. Okay, we call it projection onto, okay, onto XY plane, two-dimensional. So to get this one done, we can graph it. Just find the intercepts to graph it. You replace x, y, 0, x by 0, and that gives you y equal to the 6/3, which is 2. Replace y by 0, that gives you 3. Okay, so this is it. This is a situation in two-dimensional. So we have x equal to 2, that's going to be the intercept, x-intercept, and 3, 1, 2, 3, that's a 3. So the line is going to be this one. Okay, that's going to be the line. So the region in question, remember intersection between these and the x and the y coordinate over here. So this is going to be the region that you are going to integrate in two-dimensional for your double integral part. So decide what you want to do, type 1, type 2. So it's clear for the triangle that you go with the x between, you fix the x between 0 and, okay, did I make a mistake? Yes, sorry. That's x is 3. So this is 3. And this is 2. Okay, because this is it. So the restriction for the x is going to be, you go to the right to the left to get the x. Then you have to go up and down to get the y. You see up, down, up, down, up, down. If you go up, down, the bottom one is 0, which is going to be y equal to the 0. And the top is this line here. Okay, the top is this line. So you have to find the top. So we're going to find it. You solve for y. So you have a 2x plus a 3y equal to the 6. So that gives you 3y equal to the, okay, it's a 6 minus 2x. And you can divide it by 3 to get the y. So if you divide by 3, that gives you 2 minus 2/3 x. So your y is going to be integrated between 0 and 2 minus 2/3 x. Okay, this is the way you are going to identify the region and the limits of your integrations. Any question? So we have the limit for the z. We drop it down to the xy coordinate, x between 0 and 3, and the y. So there you are. So the triple integral that we be given, and we have a function y squared dx dy dz is going to be, you can switch it in any form that you like, or you get it over here. So the form that we created are going to be x is a constant. Okay, sorry, this is x between 0 and 3. Okay, so x is between 0 and 3, so we go with the x last, if you like. Then in the middle, you go with the y, and that would be 2 minus 2/3, 2 minus 2/3 of x. Then you have to start with the z here. Z would be 0, and 6 minus 2x minus 3y. Then you have a function which is y squared. So you do the zyx. You see, that's going to be the one. Any question? You know that those functions are nice polynomials, so you can switch the order as you need it. And according to your construction, this must be the order in question. Okay, any question? Now we are ready to do it. So we do the z first. Easy, integral of y squared respect to the z with y squared z. So it's going to be equal to the 0 to 3. Okay, 0 to 3, 0 to 2 minus 2/3 x. So you get the y squared z. Y squared z, and z goes from 0 to the 6 minus 2x minus 3y. And when you're done, you go with the y and the x. Okay, you have to substitute for the z and then continue. So this is going to be 0 to 3. Okay, 0 to 2 minus 2/3 x. Okay, substitute. This is z. So it's going to be y squared times 6 minus 2x minus 3y. Okay, 3y, and then the dy, the dx. Okay, the leftover would be, and the leftover would be 0. Okay, this is going to be the first part. So multiply the y squared inside and then integrate respect to the y. Okay, I'm done. I go to the next page to continue. So I multiply the y squared inside. That gives me 6y squared minus 2xy squared, and that would be negative 3y cubed. So I continue. So this is going to be the case. I call it I to continue my integral. So I have the 0 to 3. Okay, that was 0 to 2 minus 2/3 x. If you multiply it inside, that gives you 6y squared minus 2xy squared and minus 3y cubed. Okay, 3y cubed, then I have to find the dy dx integrating. Okay, so we are going to continue to get this done. Okay, so what is going to be the result? You see, the result is going to be when you're integrating. When you're integrating, that would be what? That would be y to the 4th over 4. You see, that would be y to the 4th over 4, and this would be again something like something like 2xy cubed over 3. And remember, you have to multiply. You have to substitute this one. 2 minus 2/3 of x and continue. If you like, you can do it, but it takes times to be able to do it, to simplify it. So you have two choices. You may go back and okay, because if you integrate respect to the x here, if you integrate respect to the x first, you see that would be simply 2x squared over 2, which is going to be x squared over 2 right away. Okay, so so it depends what you want to do. So that would be easier to handle, but it's not a big deal. Okay, to be able to do it. So one choice is, I just wanted to see various possibility, various scenario, if you like. So you may say, oh, I may have a better chance if I go back and have another look at the region that I did have, because this is going to be, you see, that is the one that you did have. That was a 3. That's a choice, and that's a 2. Remember, this is the one that you did have. So the way we did it, we fixed the x. This integral happened to be difficult. So what you can do, you can fix the y, because you don't have any difficulty here. If you fix the y, so your y would be between 0 and 2. Okay, between 0 and 2, then you have to find your x. You see? So what I did, and now I go from right to left for the x. You see, right to left, right to left. So that would be, this is going to be right to left. So this means I go from, okay, I go from 0, if you like. I go from 0 and I find the x here. Remember that equation was what? This equation was, what was the equation of the line? 2x You see the equation was 2x plus 3y, 3y equal to the 6. Okay, equal to the 6. Now we can solve it for x if you like. 2x equal to the 6 minus 3y. And if you divide it, that gives you 3 minus 3 half over y, which is much easier to handle it. This is a choice. Unless you don't like it and you go on, you get this y to the fourth here, then you get the y squared here. Okay. And because of this 2x, it would be very messy to continue with that method. Okay. So that's why you can, everybody understand what I'm doing. Any question? So if you stay with this one, that y to the fourth would be in trouble because you have to raise it to the fifth, to the fourth here, and you have a 2xy. But if you integrate respect to the x, this one is much easier because you just integrate 2x, okay? So what we can do is we can change the direction, and you start it over. You see, if you start it over, this is going to be the triple integral that we have. Intentionally, I did it so that you see what would happen, if you want to change your direction. So that was the original one. Now we can rewrite it in this format. You see, the format that we pick is we do the y at the last so that we don't have any difficulty. So that would be the y. We do the x in the meantime. We do the x in the meantime. So it's going to be 3 minus 3 half of, okay, 3 half of y. And the z is going to be as is. So the z part is going to be unchanged. Okay, so we have the function. So we do the z, we do the x, and then we do the y. So you will see in a minute that it's going to be much easier. So be prepared for it. So if you need to change the direction, change it. So the first part is going to be the same thing. You see, I do it 0 to 2, and this is going to be 0 to 3 minus 3 half of y. So that give you the same one is the y squared z. Okay, y squared z, of course, z going from 0 to, as we did it before, 6 minus 2x 3y. And then you integrate, okay, integrate respect to the x first, then the y. So if you substitute it, the resulted expression is much easier to handle. It's a 3 minus 3 half of y. You see, you get a y squared times 6, the same thing that we did have before, but this is going to be dx dy. You see, this is very easy to integrate respect to the x, even you don't have to multiply it. Because this is a constant, you integrate the inside respect to the, okay, you integrate. So this is going to be a situation that we're going to have. Okay, if you want, you can multiply it first. So you have only one term containing the x. So that gives 6y squared minus 2y squared minus 3y cubed. Easily can be integrated respect to the x, and the rest, the next part is going to be also easier. Okay, integrate respect to the x. So that gives 6xy squared. That gives you minus 2xy squared. And this would be minus 3xy cubed. Then you go from x equal to the 0 and x equal to the 3 minus 3 half y, and then you integrate the y at the end. Okay, so that's the advantage of switching your method. And the rest are going to be easy to handle. This is, so I have a 6y. So integrate respect to the, I just double check to make sure I get everything all right here. So that's a 6y squared. That was integrated respect to the x. I made a mistake here because I missed the x here, sorry. That's the x. So here now I got the x squared over, you see that's what. It's a 2x integrated with respect to the x would be 2x squared over 2. So that gives x squared y. X squared y, and the rest are going to be all right. Okay, I missed that 2x that we get. Okay, so that's it. Yes, you are right. I missed the x. I correct that. Now continue. If you put the x0, we get nothing. If you put the other one, so this is it, is going to be 0 to 2. 6x, this is x. So 6y squared times, it's all, well, it's going to be polynomial. 3 minus 3 half of y minus x squared, it's going to be y squared times 3 minus 3 half of y squared. Okay, minus 3y cubed times 3 minus 3 half of, okay, 3 half of y. And everything is going to be in dy. Okay, so that would be easier to handle. We can simplify it quickly. You see, a different way to simplify it. If you like, you can factor out this or just multiply them together. So if you multiply them together, lots of things, these would be cancelled out because of the term that we have. Okay, so I just give you the simplifications that I've done. So this is going to be 0 to 2, 0 to 2. Then you arrive at the 9y squared minus 9y cubed. You can check it, but it's correct. Okay, and this is going to be the dy. Okay, you multiply lots of these terms would be cancelled out. And then this is going to be the final answer. Then you integrate it, which is very easy to integrate. So it's going to be 9y cubed over 3 minus 9y to the 4th over 4. Then you go from 0 to 2. 0 to 2. If you put the y equal to the 0, we get nothing. If you put y equal to 2, you can simplify it easily and get the result. Okay. So substitute. So this is going to be, if you put the 0, we get nothing. So it's going to be 9 times 2 cubed, 2 cubed over 3. And this is going to be minus 9 times 2 to the 4th over 4. Okay. This is it. So 9 over 3 would be 3. 2 cubed would be 8. 3 times 8 would be 28. So I put it over here. It's going to be equal to the 28. Okay, 2 cubed would be 8. 3 times 8, 24. Minus 2 to the 4th, 16. 16 over 4, 4. 4 times 9, 36. So the final answer is negative 12. And I give you the result. Okay, if you check assignment, this is one of the problem in your assignment. And just pick this one to explain this idea that you may have to switch your order after integrations, okay, to be able to do it. That would be very hard to continue to get that y to the 4th. Okay, so that's the point about this problem. Any question? So the tetrahedron, if the function is going to be just if you want to find just the volume problem, it would be easy because you are not going to have any function. Okay, you get just one, but this situation was a little bit different. I wanted to get the experience. Okay, that's first one. Any question? So that was a point about this problem. Now we go to the second one. They ask you to use a cylindrical coordinate to find the volume of a solid. So we give you one problem using the cylindrical coordinate. We have quite a lot over here, but it's nice to practice. So number 2. Okay, the number 2, we would like you to use, so the instruction is given to you, use a cylindrical coordinates to find the volume. find the volume. Okay, the volume of the solid. Okay, to find the volume of the solid bounded by it's going to be bounded by z equal to 9 minus x squared minus y squared and z equal to the 0. That's it. Easy structure. They give you the instruction to do the cylindrical coordinates. So you set up the volume first. You know that in the triple integrals, you can set up the volume by using 1 as your function. So you must know this one to start with, solution. So the volume is going to be triple integral on the region that we have, or the solid, we call it G, whatever. Okay, and this is going to be 1 dV. So that's a formula for the volume in 3-dimensional. Again, you have to set up the limit of integrations. You like to see, you set it up to see what's going on. And then you just use the polar coordinate to find it. And so we check to see if any Z is given. Yes, the Z is given to you. So we have the Z. So we have the note that Z is going to be between 0 and 9 minus x squared minus y squared. So that is going to be the Z. So we get the projection on the XY plane. Okay, so this is it. If you put the Z equal to the 0, so you go to the 9 minus x squared minus y squared equal to the 0, and that would be x squared plus y squared equal to the 9. Okay, so that would be a circle centered at 0 with the radius of 3. Okay, that's it. You know that since you want to do the cylindrical coordinate, in the case of cylindrical coordinate, you fix the Z, which is fixed. Then for the projection into the XY plane, you're just using the polar coordinates. So this is going to be your projection into the 2-dimensional. Then the polar coordinate of the circle is going to be the fact that the R is going to be between 0 and 3, the radius, and the data is going to be between 0 and 2 pi. So that's it. If it's not going to be cylindrical coordinate, you know that you'll be in trouble because you have to, you get the semicircle to the top to the bottom, you put this top bottom, negative radical 9 minus x squared, and then the range for the x. But it's a best way to do it is just the cylindrical coordinate. Okay, so we are ready to set it up. So cylindrical coordinate of this triple integral is v equal to, okay, it's going to be 1. We go last with the data is going to be 0 to 2 pi. In the middle, we go with the R, 0 to 3. And we go with the Z. So the Z is between 0, okay, this is it. Z would be 0 and 9 minus x squared minus y squared. You have to write this one in polar form. That would be 9 minus R squared. Okay, because you are in cylindrical coordinate and leftover must be in terms of the R and the data. Then your function is 1, but the extra term, remember extra R, Jacobian, now you know it. Extra R for the polar, and then usual, this is it. The usual one is Z is fixed, dz. In the middle one, you go with the R, and in the last part, you go with the data. Any question? So for the cylindrical coordinate, it depends how you set it up, the problem. So we go with the Z first because the Z is fixed. Then the rest is going to be polar coordinates. Okay, now integrate, start integrating respect to the z, which is going to be easy. It's going to be 0 to 2 pi. Okay, 0 to 3. So the integral of the r to rz. So it's going to be rz. Then the z going from 0 to 9 minus r squared. Then we have the drd data. Substitute. So that gives 0 to 2 pi, 0 to 3, r times z, r times 9 minus r squared. And the leftover is going to be 0. Then we're done, it's a drd data. So we then multiply it and then integrate it. Okay, we multiply it, it's going to be 0 to 2 pi. And that's going to be 0 to 3, 9r minus r cubed. Then the drd data. Okay, integrate respect to the r. 9r squared over 2, and that's the other one. So it's going to be equal to integrate in respect to the r, 0 to 2 pi. So that gives us 9r squared over 2, 9r squared over 2, minus, that gives you r to the 4th over 4. Okay, and this is it, your r going from 0 to 3. Then you come back and do the d data. So substitute 0 to 2 pi. Put the 3 first. It's a 9 times 3 squared over 2 minus 3 to the 4th over 4 minus 0, nothing else. Then the d data. Simplify these numbers. 3 squared would be 9. 9 times 9, 81. So 0 to 2 pi. So that gives 81 half. Minus 3 to the 4, 81 again. 81 quarter. And you know, it's going to be 1/2 minus quarter. It would be just a quarter again. So it's going to be 0 to 2 pi. 81 quarter d data. Okay, you put it out, and the leftover is going to be 81 over 4. Data is going from 0 to 2 pi. Okay, so it's going to be 81 4 times 2 pi. You soon find the 2 and the 4. So the final answer is 81 pi over 2. That would be the volume. Okay, it's a nice problem. Just to show you how you're going to set up the cylindrical coordinate. So you receive one cylindrical coordinate on that, on the test and on the final. Okay, any question? So that was number 2 on that. Then we go to the 3. You have a similar one on the extra 3. Just check them. So let's see what's going to be the problem number 3. Okay, the number 3 is just finding a triple integral again on the curvilinear region, if you like. This is it, number 3. Let's see what is special about this one. You want to evaluate this integral. Evaluate the integral is triple. That's it. 1, 2, 3. The function is y. Okay, it's going to be y dv. We're going to y dv on the solid g. What is the solid? Solid is enclosed by, so it's going to be where the g is the solid. G is the solid. Is the solid enclosed by a plane? Closed by, it's closed by the plane. By one plane with the equation of z equal to y. Okay, this is the one, and xy plane. xy plane. You know that xy plane would be z equal to the 0. That's the xy plane and a parabolic cylinder. And the parabolic, that's it, sorry, parabolic cylinder. Cylinder is y equal to the 1 minus x squared. That's it. Again, setting up this is going to be important for us. This is it. So it's a triple integral. Okay, so you have to find the limit of integration. So you start with the z. You collect the information that you have about the z to make it the limits of integration for the z. You have one plane over here, z equal to the y, and you have the xy plane. So the xy plane is going to, so the g is going to be, you see the solid consists of the following, consists of the z equal to the y, okay, xy plane is z equal to the 0, okay, and this parabolic cylinder. This is what you have. Okay, so z is clear. So we get the fact that the z is going to be between 0 and y. Whatever number you have two numbers, you collect them together, that give you your z. Okay, you drop it down in two-dimensional to get these numbers. So if you put the z equal to the 0, okay, that would be interesting because you want to drop it down to see what is going to be on for this. Okay, so the projection onto, see the projection onto the xy plane is the fact that you already got this y equal to 1 minus x squared, but you see the situation is going to be this. To get this projection, we let z equal to the 0. You see we get the z equal to the 0. To go back into the two-dimensional, if you put z equal to 0, you see z is also equal to the y. So that gives you y equal to the 0, and you have a y equal to 1 minus x squared. Okay, so what does it mean? This means the region in two-dimensional, you see this is going to be the two-dimensional case is you have, if you intersect these together, so this means basically you have 1 minus x squared equal to the 0, so x squared equal to the 1, so x would be positive negative 1. So that gave you an idea what, because this is it, y is 0, y, this is going to be 1. Look at this one. Okay, y equal to the 0 is going to be the x-axis. Then you have to get this parabola, y equal to 1 minus x squared. And we already get the intersection here. So we have the 1. You see it's going to be a positive 1. This is going to be a negative 1. Okay, it can have negative 1, positive 1. You know that it's going to be curving down. And if you put x equal to the 0, that gives you 1. So this is going to be, okay, so that's a negative 1, and this is going to be the 1. So this is going to be the region or the projection in two-dimensional. Any question? Okay, we know that we have this y equal to the 1 minus x squared, which is going to be a parabola, but the intersection with the x-axis, so that gives it 1. So get the limits, type 1, type 2 region. It's clear that you go to the left, to the right. So you better pick the x to be between negative 1 and 1, and then you go up and down. Type 1. Type 1 region is the best way to do it. So the x would be negative 1 and 1. Okay, in order to get the y, we go up and down. You see, up, down, it's going to be all y equal to the 0 and the y equal to the 1 minus x squared. Okay, so your y is going to be greater than equal to the 0 and less than equal to the 1 minus x squared. And you already decided about the z. That's it. So this is type 1 region, if you like. Okay, type 1 region for the projection. Okay, now we set up all the information we need. So go back, form the triple integral. It's very easy integral to find. Have nothing to worry about. Okay, any question? So again, we wanted to give you the chance to see different format, different scenarios. Okay, so then we're ready to do it. Okay, let's set up the integral. That's the triple that we have. So the way we design it, x is the last to integrate. Y is going to be in the middle. And the z is going to be the last one. Okay, z is going to be between 0 and y. And the function is a dy, so it's going to be dz, dy, dx. Okay. Easy integral to handle because this would be just yz, and the z is y, make it to the y squared, then we can handle the y squared here. Okay, so this is it. It's going to be negative 1 to 1, and that's a 0 to 1 minus x squared. So we got the yz, z going from 0 to y. When we're done, we get the dy dx. So that make it to only y squared, so negative 1 to 1. Okay, is 0 to 1 minus x squared, just y squared. Okay, that's a y squared dy dx. You know, y squared would be y cube or 1/3. Okay, this is going to be equal to. So we keep the negative 1 to 1 and we integrate respect to the y. So that gives me 1/3 of the y cubed, but y going from 0 to 1 minus x squared, then the dx. Okay, so it's going to be equal to, we can pull out the 1/3. So it's going to be the 1/3 integral from negative 1 to 1. When you substitute, that give you 1 minus x squared all cubed dx. Okay, you have to cube it to get this. If you know that a cube of a binomial, you do it. Otherwise, you know, you multiply it to get these numbers. Okay, you have to use this identity that a minus b all cubed is going to be a cubed minus 3a squared b plus the 3ab squared minus b cubed. That's a cube of the binomial. Otherwise, you know, you can multiply it. You can square it, then you multiply by 1 minus x squared if you don't remember that formula. So if you do it, this is going to be the case. Let's see if I can write it down here so that you have it. So it's going to be equal to the 1/3 integral from negative 1 to 1. If I apply that theorem, cube of the first one would be 1 minus 3 times minus 3x squared. Okay, that's first one, then 3 times the square of a second times first, so it's going to be plus 3 to the 4th. And the last one minus x to the 6th. X to the 6th dx. So this is the way you operate. Okay, it's easy to integrate and substitute. If you integrate it, you just move those powers up. So I just put it's going to be 1/3. And when you integrate it, that gives you x. This would be 3x cubed over 3, which is going to be x cubed. And this is going to be 3x to the 5th over 5. And it's going to be minus x7 over 7 to be evaluated from negative 1 to 1. That's it. It's going to be the odd function. If you substitute 1 would be enough. You multiply by 2. So the final answer, I just give you, check it for yourself. 32 over 105 is going to be the final answer. Okay, so again, setting up that problem is your main concern to be able to do it. So these are a kind of abstract. Uh, we stay with the rectangular coordinate and we're just taking the integral. So we give you two problems. One of them is just the limit of integration would be given to, or the triple integral, and you just use those iterated integral to find it. The other one is the one that you have to set up the region for us. Set up the region to get it. That would be two problems on this. A triple one, then you get one with a cylindrical, one with a spherical, and one change of variable. That would be all the 5 or 6 questions. Okay, let's go on. That's number 3. Any question? So number 4 is a spherical. You've been asked to find an integral using a spherical coordinate. It's usually a straightforward problem. So that would be a question on that, a spherical. So that's a number 4. Okay, number 4, you want to use a spherical coordinate. Okay, so use use a spherical coordinate. Spherical coordinates to find this integral, to evaluate this integral 1, 2, 3 on the solid G, and this is it, 1 over the square root of x squared plus y squared plus z squared, which is nice, and the dv. Okay, dv, where what is G? G is a sphere, where G is the sphere with the equation of x squared plus y squared plus z squared equal to the 25. The region is nice and the symmetric form of the equation is nice. So automatically it must be done by the spherical coordinate. Okay, in a spherical coordinate, you know that you have to check the equation of your solid. Okay, the region that you have. The region is easy, it's a sphere. Since it's going to be a sphere, so the radius is 20, the radius is 5, so quickly that give it a row. Okay, the row would be between 0 and 5. Then if you project it, z equal to the 0, the leftover is going to be a circle. So it's a circle in the polar angle is data between 0 and 2 pi, and the declination angle phi is the usual one, the angle between two lines. In that case, phi would be between 0 and pi. Okay, so there is nothing unusual about this one. Okay, so this is how you set up the solution. So your solution is that the G is just a sphere, x squared plus y squared plus z squared equal to 25. So that quickly give you the fact that you know that you replace this by rho squared is equal to the 25. So that give you the fact that the rho is equal to the 5. So you're integrating for the rho between 0 and 5. Okay, so that's the first part. Then projection into there. Okay, that's it. Projection onto XY plane. There is no other Z, so you have only one Z. So that gives you Z equal to the 0. Z equal to the 0 resulted in x squared plus y squared equal to 25. A circle. 5, 5, 5. Okay, negative 5 and 5. So no restriction. So data is going to be between 0 and 2 pi. And the phi is between 0 and pi. Okay, so we have everything we need. So we go back, we set up the The integral in a spherical coordinate, you have to change the function. The function is nice. So this is how we're going to handle it. The given one is this one. Okay, x squared plus y squared plus z squared. So we change it. We do the data at the end, so it's going to be 0 and 2 pi. We do the phi in between, 0 and pi. You can switch it, doesn't matter. And we do the row first. The row is between 0 and 5. We switch the function into the polar form, into the spherical form. In a spherical form, this is going to be rho squared. So it's going to be 1 over the square root of rho squared. Extra term, Jacobian. Extra term for the spherical coordinate, you can bring this formula. Okay, or the formula for the cylindrical or spherical because you need them. So the extra one is rho square sine of the phi. And then you integrate, the order is going to be d rho. Okay, d rho, d phi, d data. You know, the way we wrote it down. Okay, so we simplify it. So this is going to be simply, this is going to be rho and one of them would cancel out. So we end up with this integral. So this is going to be 0 to 2 pi, 0 to pi. Okay, 0 to 5. So the leftover is going to be just 1 rho on the top, rho sine of the phi. Okay, rho sine of the phi and the d rho d phi d data. Integrate respect to the rho, it's going to be rho square. So it's going to be 0 to 2 pi, 0 to pi. Okay, rho square or 1/2 of the rho square. Then rho going from 0 to 5. 0 to 5, and when we're done, multiply by the sine of the phi, and then take the d of the phi, d of the data. If you put the rho equal to the 5 times 5 would be 25, so we can put it out. So it's going to be 25 half. Okay, 25 half. 25 half, so the leftover is going to be 0 to 2 pi, and the 0 to pi. Now we're integrating sine of the phi, d of the phi. Then when we're done, d data. Now we integrate respect to the phi. Integral of a sine is a negative cosine. So it's a 25 half, 0 to 2 pi, negative cosine of the phi. To be evaluated from 0 to pi, and then d data. Okay, you substitute, you should get 2 here. So it's a 25 half. Okay, move it down. It's going to be 25 half, and you substitute 0 to 2 pi. So if you put the pi, that gives you negative cosine of the pi minus negative cosine of the 0. You know that the cosine of the pi is a -1, and this is going to be 1. So it's going to be 1 and 1, which is going to be 2. So it's a 25 over 2, 0 to 2 pi. And because negative would be positive and the positive. So that gives you 2 d data. So these 2 would cancel out. So you integrate the leftover, that gives you 25 data. 25 data from 0 to 2 pi. For the 0, we get nothing, and 25, you get 25 times 2 pi. So the final answer is 50 pi. 50 pi would be the final answer. Okay, so in the case of the spherical one, most of them are going to be integrated on a sphere. There is one which is not, it's very tough, and we have it. and we do it later. But otherwise, most of them can be done easily. Okay, so you have to, you need to bring, if you like, the formula for the spherical coordinate, because you are going to get, you get one of them. Okay, so this is one for the spherical one. Any question? Let's do one more. The next one is we have a group of integrals that we want to do it using the cylindrical coordinates. Okay, so not bad for the cylindrical. You have all the different collections that all the possible really. And this review is a very good one. When you put them together with your extra one, you can't find any other problem, if you like, of this group. So let's study this one and then you should be fine. So in this problem, they give a couple of integral and they ask you to use a cylindrical coordinate to do it. So we give one cylindrical, these are for practicing. Use cylindrical coordinates to evaluate these integrals. These are the integral that the limit of integration is already given to you. So you don't have to. The limit is not this. The domain is not described, but it's given. So use a cylindrical coordinate to evaluate these integrals. So the first one is, we call it part one. The part one is this one. So the integral from -2 to 2, 0 to 4 minus x squared, and the top is 0 to 1 over x squared plus y squared. The function x squared plus y squared, and the dz, dy, dx. That's it. Remember cylindrical coordinate. You have a fixed z, and if you go to the two-dimensional polar coordinates, and you can see this polar coordinate right away. Radical 4 minus x squared is a semicircle. It's a semicircle. You go from -2 to 2, so easily can be, okay, can be format if you like to get it. For the z, this is going to be the range of the z. So as usual, it's clear everything, but we have to set it up. Solution. So get this information that you have. They do the x right at the end. So your x is between -2 and 2, and your y is between 4 minus x squared. Okay, this is going to be the case, and the z is between these numbers. Z is easy, we can substitute it right away. So we have to get this, that this is going to be y equal to the radical 4 minus x squared. So you have x squared plus y squared equal to 4. But y is positive, means just a semicircle. Okay, so this is going to be the one. So this is your projection. The radius of 2, but only the top. You see, this is going to be the case. It's only a semicircle. So if you want to change it to the polar form, and the x is between -2 and 2, so it's going to be all the top. So in this case, your r is going to be the radius between 0 and 2, but your data is going to be only between 0 and pi, because it's half a circle. If they give you negative radical 4 minus x squared from here, that would be the full circle. Okay, so the rest can be handled, because you have to change this one into the polar function. X squared plus y squared is r squared, and you have to change the z into the pole, which is easy, 1 over r squared. Okay, so we can go ahead and set up the integral. Any question? So call it I and do it. So this is it. We are going to set it up that integral. So it's going to be equal to the polar part. The polar part, the data is between 0 and pi. And the r part is between 0 and 2. Then the z part, we have to change the z that we have is 0, 0. It's 1 over x squared plus y squared, which is r squared. Or you know that you substitute x equal to the r cosine of the data or sine of the data. But these are easy, so we don't have to substitute. We know it. And again, here you have to change it. It's going to be a square root of r squared. Then extra r, extra r. Extra r, then you integrate it respect to the z first. Okay, that's it. Z r data. Any question? So it's a nice one. This would be r. So r times r would be r squared. So it's 0 to pi, 0 to 2, and it's going to be 0 to 1 over r squared. But the function is going to be r squared dz dr d data. Okay, we integrate that, give you 1 r squared over 2. Okay, so it's going to be equal to 0 to pi, 0 to 2. So that gives you 1/2 of, or 1/3 of r cubed. Okay, 1/3 of the r cubed, and the r going from, oh, I'm sorry. I integrate respect to the z. Sorry, I made a mistake. Integrate respect to the z would be r squared. Okay, r squared. I haven't done the first part yet. Sorry about that. Okay, integrate respect to the z. Integrate respect to the z. So that gives us r squared z. R squared z, and z going from 0 to 1 minus 1 over r squared. Then we come back and we do the r and the data. Okay, we have to do the z first. When you do the z, you replace the z by 1 over r squared, and that's simplify everything for us. 0 to pi, 0 to 2. So it's going to be r squared times 1 over r squared. And then we get the dr d data. So these two will cancel out. We get the 1. So it's going to be 0 to pi, 0 to pi, 0 to 2, just 1. dr d data. Okay, integrate respect to the r would be r. So it's going to be 0 to pi. And this is going to be just r. 0 to pi r, sorry. Integral would be r, so r going from 0 to 2, then the d data. So that's just simply give you 2, 0 to pi 2 d data, which is going to be 2 data from 0 to pi. So the final answer is 2 pi. Okay, so the result of the integral is 2 pi. So it's it's a nice format. Okay, so let's have a break now. Have a break. We come back and we do the rest. There is one more of this cylindrical one. It's not bad, but there is a one point about it that you may be surprised. So we have to do the part B, then we keep going to get the rest. Okay, 11:56. Okay, let's come back at 12:10. Be able to do the rest. We should be able to do the rest that we have. Okay, see you then. Okay, so we are going to continue. We were working on the finding the integral by using cylindrical coordinates. Okay, that's number 5.1. There's another one. This next one, just there is a technical point about it. So again, using cylindrical coordinate to evaluate this integral. So part B, and the integral is this one. Integral from 0 to 1. Okay, 0 to 1 is a negative square root of 1 minus x squared to the 0. And then it's a negative x squared minus y squared to the x squared plus y squared. And the function is this, 21x y squared. Okay, dz, dy, dx. Okay, that's the integral that you want to change it to the, okay, to the cylindrical coordinate to do it. Again, you're just focusing on this xy plane projection. The projection is going to be easy because this is y equal to the negative 1 radical minus x squared. You end up with the x squared plus y squared equal to 1, which is going to be unit circle, but you got to be careful because you go 0 to 1 over here. So you are not going to have the full semicircle. So it's going to be just a quarter of that. So that part is interesting. The other one is changing the function. You know that when you do it, you have to change the function because the z is going to be fixed, but z is going to be a function of r and theta. So this would be easy. X squared plus y squared is r squared, and this is negative r squared. But the difference is here. You see it's a 21xy squared. The one that we did usually was x squared plus y squared. You can change the r, but you should be prepared. If you see this one, doesn't matter. Just substitute from the polar form, x equal to the r cosine of the theta and y equal to the sine of theta, and patiently take that integral. So it's a little bit different because of this format, and we want you to make sure that you practice this type of ideas too, okay? So there you are, checking this xy, the polar form. So from here, we have the x is between 0, 1. Okay, from the second part, you have that the y is, this is the y. Okay, so you let it y to be equal to the negative 1 minus x squared. And as usual, square it, move it to the other side. That give you your unit circle. Okay, then check this unit circle to what, which part are you going to be interested in. So since, and remember the y is negative. So this means you are interested in the semicircle, but this is going to be the bottom part, not the top part. So this is, make it a new. So if you get an image of a unit circle, okay, the radius of a negative 1. So this is going to be radius of 1. So this is the case, and this is 1. So what you are going to consider is going to be just the bottom one you are interested in. Okay, this is going to be the one. But then you check to see what's the restriction on your x. Restriction of your x is between 0 and 1. Since x is between 0 and 1, you are not going to have all the full semicircle region. You have only the quarter. Okay, this is going to be, so this is 0 and this is 1. Okay, 0, 1. So you are going to be interested in this part. Okay, so you are going to be interested in this part. So your r is clear. So your r is just the radius. So the r would be between 0 and 1. Okay, this is going to be your r. Then you have to pick the data. What is going to be the data that you're going to pick to represent, okay, represent this region over here? That's the one that you have to be careful again. You see the The direction that we consider is going to be a counterclockwise. And remember, x is between 0 and 1. So between 0 and 1 means you go in this direction to get it. Okay, that's going to be the 0 and 1. So when you go in this direction, 0 and 1, so your angle is going to be what? So if we start from here, this angle would be negative pi half if you like. So pi half going to the 0. So it's going to be greater than equal to the negative pi half. And is going to be less than equal to the 0. So that's the way you are going to pick the data. Okay, any question? So you got to be careful to your value should be representing this region correctly. Okay, and so you cannot pick that, you know, something like 3 pi half, because you're going in this direction, then that doesn't make sense. So that's why you have to go with the negative pi half and the 0. When you write your integration, then everything would be making sense. Okay, any question? Now we are ready to put it together. We don't have anything for the z because we can substitute. So the original one, call it I and change it. So we change it, you know that as usual, we go with the phi at the end. Data, for example, this comes negative pi half to 0. Then you go with the r, radius between 0 and 1. Then for the z, whatever you have here. So for the z, this is going to be negative r squared. And this is going to be a positive r squared. Then you have to substitute to get this because they are unusual. They are not just a regular one. So it's going to be 21 times x. X is r cosine of the data. Okay, r cosine of the data. Y squared. Y is r sine of the data. All square. Remember, when you do the cylindrical coordinate, there is an extra r. There is an extra r, and then you're integrating respect to the z, respect to the r, and respect to the data. So this is the way you are going to set up this integral. Now you have to do a little bit of algebra to see what's going on for this one. Okay, so you have to square this. Okay, so this is going to be, if you square it, that gives r squared sine square of the data. So I'm going to collect these r's together. I have the r squared r that give me 4, and I'm going to bring this 21 outside to make a room for the others. Okay, that's it. Negative pi half is 0, and that's going to be 0, 1. So it's end up with r, that's r squared, and this is going to be r to the 4th. Okay, so r to the 4th, and I have a sine squared. This is it, sine squared of the data, cosine of the data. Okay, and then we start integrating by, okay, I integrate respect to the z first, then the r and the data. Okay, integrating respect to the z would be easy. Just put one z here, and oh, I'm sorry, I haven't done the z yet, so it's going to be the triple one. It's a negative r squared to the r squared. Okay, 1, 2, 3. I just simplify the middle one. Now we continue to integrate respect to the z. Respect to the z, there's going to be just extra z here. Everything else would be the same. 21, negative pi half to 0. Okay, then 0 to 1. Then you are going to have a z, and just the rest are going to be unchanged. R to the 4th sine square of the data, or cosine of the data. Okay, then z going from z going from negative r squared to the r squared. Then you come back and we go to dr data. Okay. Now, when you substitute, that's it. You put the r squared and then minus this one. So this is going to be, in fact, 21 as is. This is pi, negative pi half to the 0, 0 to 1. Okay, so what's going to be the leftover? So you have the r to the fourth sine square of the data, cosine of the data. Then when you substitute, you get the r squared minus negative r squared. Okay, dr d data. Then these two would be 2r squared, and you multiply by r to the fourth. So that gives you 2r to the 6. I multiply the 2 by 21, make this one into the 42. So the integral from negative pi half to 0, integral from 0 to 1. Okay, now I have r to the 6. R to the 6 sine square of the data, cosine of the data, then the drd data. Okay, so that is not going to be a big deal. We integrate with respect to the r, that gives r to the 7. It's from 0 to 1, so that gives you just something like 1 7. Okay, so this is going to be equal to, I put the 42 as is, the integral from negative pi half to 0. R to the 6 would be r to the 7. So r to the 7 over 7. Okay, and r going from 0 to 1. Then the leftover is going to be sine square of the data, cosine of the data, and the d data. Okay, if you put the one that gives 1 7, I bring the 1 7 out. So that give me 42 over 7 and the leftover for the integration. Okay, are you done? Any question? So we can, even you can simplify the 7 and 42 here. Okay, so that gives us 6 outside. 6 outside, 0 to 1, make it into nothing. Okay, so this is going to be equal to, so you end up with a 6 integral from negative pi half to 0. Nothing else but sine square of the data, cosine of the data, d of data, which is easy to integrate because if you call this one u, so u prime is already there. So it's like u cubed, u squared. It's going to be u cubed over 3. So it's going to be equal to 6 sine cubed of the data over 3, and the data going from negative pi half to 0. Okay, that's it. If you put the 0, sine of 0 is 0. So you won't get anything. You see, you can simplify this too. So that gives you 2. So we get a 2 sine cube of the data. And this is going to be between negative pi half and 0. So that's it. 2 sine cube of the 0 minus 2 sine cube of a negative pi half. Sine of the 0 is 0. So this would disappear. Sine of the negative pi half is a negative 1. Negative 1 cube is a negative 1. Negative would be positive. So the final answer would be 2. Okay, so this is going to be, that's it. It's going to be negative 2 times a negative 1 cubed. So the answer is 2. So the integral is equal to the 2. Okay, so it was interesting, is a little bit different from the other, especially the operation inside. So be prepared for it. You may not get something straightforward, x squared plus y squared to the r squared, but it can be, it can be handled to get these numbers. So that was another one for so that is a cylindrical coordinate type. Okay, any question? Number 6 is straightforward. It's just easy integral you want to find. Let me see. Number 6 is just a triple integral on a box. So one of them would be given to you, but in this case, it's not difficult, but I do it. So number 6, you just want to evaluate this integral, a triple simple integral on a rectangular format. So that's it. Triple on the solid G. And you have x, y, sine of the y z dv. So where z, where g is just a rectangular box. Okay, it's just the original. It's going to be the rectangular. Okay, rectangular box defined by the following. Okay, so you have the x is between 0 pi, y is between 0, 1, and the z is between 0 and pi 6. Not a big deal, but you got to be careful when you want to integrate it right at the beginning. Got to be careful about these integrations, but otherwise it's a straightforward problem. Okay, let's set it up. Any question? Are you ready? This is it. X is between 0 pi, y, and the z. So it's a box. So the integral is going to be solution. So we get a box. So x 0 to pi, y 0 to 1, z 0 to pi 6. And the function xy, sine of the yz. Okay, yz, we go with the z first, z, y, x. Okay, we integrate respect to the z first, that would be easy. You must make sure that you know that the integral of a sine would be negative cosine, but you have to divide it by y prime. In this case, if you differentiate respect to the z, the result would be y. So this is how you are going to do it. So it's going to be 0 to pi, 0 to 1. So that would be xy as is. Integral of a sine is cosine. And you have to multiply by can of q prime. So this would be y. Then z goes from 0 to pi 6. Any question? Then the dy dx. Because when you differentiate the top, u prime would be y. So we put the y here to cancel it out. Now the y would cancel out. So you get the 0 to pi, 0 to 1. You get the x cosine of the yz. But the z is between 0 and pi 6. Dy dx, rather unusual one, but it's fine. Because you put the pi 6. Okay, so it's going to be 0 to pi when you substitute. If you put the pi 6, that gives you x cosine of the pi 6y. Pi 6y. Okay, pi 6y. Then it's going to be minus, minus x cosine of 0. Okay, then we get the dy dx. I miss a negative sign somewhere. You see that is integral of a sine is a negative cosine, sorry. There is a negative here. So I'm going to pull out that negative here. Integral of a sine is a negative cosine, so I need to have a negative here to make it. So I put it at negative, so I carry this negative for a while. Then cosine of 0 is 1. Okay, cosine of 0 is 1, so we end up with this. It's a negative 0 to pi, 0 to 1. Now you have to integrate x cosine of the pi 6. Y minus x, minus x, integrate respect to the y, dx. Okay. And so it's going to be equal to negative 0 to pi. Again, you keep the x, you integrate cosine. Integral of a cosine is sine, but it's a sine of the pi 6 y. So you have to divide by u prime, which is a pi 6. So this is going to be integral of a cosine of the pi 6 y. Any question? When you differentiate it, you multiply by pi 6. When you integrate it, you divide it. Okay, then integrated x, that give a minus xy. Minus xy, but the y going from 0 to 1, and then the dx. Okay, if you put the, so this pi 6, you flip it if you like, that gives 6 over pi. Okay, so that's going to be the 1, and then when you put the 0, everything would be 0, but you have to check the 1. So this is going to be equal to, just simplify it, and then you continue. So it's going to be equal to the negative 0 to pi, 0 to pi, and that give you, if you use the reciprocal, that gives 6x pi. Okay, 6x pi sine of the pi 6y and the minus xy. Okay, this is going from 0 to 1, y equal to 0 to 1, and when you're done, it's a dx. Okay, so if you put y equal to 1 over here, if you put y equal to 0, you get nothing, but if you get y equal to the 1, this can be done because the sine of the pi 6. So I'm going to go to the next page to continue to get it. Again, not difficult, but I just wanted to see when you get this, something like cosine of the pi 6y, know how to handle it. Okay, so substitute y equal to the 1 and then continue. So it's going to be equal to, okay, it's going to be equal to for the last integral is a 0 to pi. Okay, so if you put the y equal to 1, so if you put the y equal to the 1, that gives a negative 6 pi, and that gives us the sine of the pi 6. Okay, this is when you put the y equal to the, okay, and that's it. And then minus, so I bring this negative 1 out as I did it. So it's going to be minus xy, you put y equal to the 1, so that gives you just y, just x. Okay, and the dx, that's it. I replace y by 1, this is all I did. But the sine of the pi half is 30 degrees, so the sine would be 1/2. Okay, this would be 1/2. So you are going to have a negative 0 to pi, 0 to pi, and this is going to be 6x pi times 1/2, then minus x, and dx, you integrate it. So the 2 and the 6 would be simplified. So you end up with negative 0 to pi. That would be, okay, 3x pi minus x dx. Now integrate to get this done. So this is going to be negative. If you integrate it, that gives you 3x squared over 2 over the 2 pi minus, okay, minus x squared over 2. This is going to be the case. That was a negative, yes, it's correct. Okay, and x going from 0 to pi. Just substitute, you put the 0, you get nothing. If you put the pi, you know, you get something. This is it, 3 pi squared over 2 pi minus pi squared over 2 minus 0. 3 pi squared minus, okay, this is going to be, everything seems to be all right. Then I can simplify the top and then you're done. Okay, so what can you do is you can use your calculator or just just put these together to get the final. I just simplify it. So that give me 3 pi over 2 plus pi square 2. So that give you the final answer. Okay, you got to be patient when it's only numbers. Sometimes it's going to be messy, but I picked this one because of that. Okay, that sign that you saw. So this is going to be number 6. We give you one finding the integral on this type of rectangular region. Number 7 is again, it's easy problem, but the region, you get the description of the region. So we're just setting it up for you to just make sure you understand it. Are you ready? So I'm going to go to the next page because I need more room to do this one. So number 7. Number 7, we want to evaluate this integral. Evaluate this integral 1, 2, 3, g, and you have the x, y, z, dv. So what is g? It's very similar to the one that we did. G is going to be a solid in the first octant. G is the solid. Okay, is a solid in the first octant, so everything is positive. First, okay, first octant that is bounded by the following. Okay, that's bounded by the previous one we did. It was a parabolic cylinder. So this is similar, but the coordinates are different. It's bounded by the parabolic okay, cylinder. And this time you have a z equal to. The other one was y equal to. That's the only difference, okay? And the planes. And the planes is going to be the plane z equal to the 0. This is one of them. Y equal to the x. And y equal to the 0. You want to make sure that you read this information correctly, really. Otherwise, the integral is just a straightforward one. Okay, so it's very similar to the problem, I think, number 5 that we did. Okay, so you set up the integral. It is in rectangular form. So you have to identify the range of those 3 variables. You look for the z to see how many values do you have for the z. You have to z equal to the 2 minus x squared and z equal to the 0. So z is done. Z is going to be between 0 and 2 minus x squared. That's a z. Then you have to get the projection to see what's going on. The projection is important over here. You put the z equal to the 0, you drop it down. If you put the z equal to the 0 over here, so that gives you x squared over 2. So x would be between negative radical 2 and positive radical 2. And you are in the first octant. So x must be positive. So your x would be between 0 and radical 2. So that would be the x. When you are in 2-dimensional, you have the line y equal to the x. We just get this line with the x-intercepts. Then we can set it up and then be done. Okay, so this is was the summary. So we put it in action. So what's going to be your g? Okay, there you are. I just introduced the g. So the g is going to be, this is the parabola, 2 minus x squared. You have the z equal to the 0. Then you have the line in 2-dimensional, and you have the x-axis. These are all the information summary. So we look for the z numbers, we find it. So z is between 0 and 2 minus x squared. So that is your z. Okay, projection on the 2-dimensional. Projection okay, onto the two-dimensional that we have onto XY plane. Okay, so the number for the Z are 2, so you have to get the cross section. So it's Z equal to the 2 minus X squared, Z equal to the 0. So in this case, that give you 2 minus X squared equal to the 0. So that give you X squared equal to 2. So X would be positive radical 2. But remember, you are in the first octane. First octane, everything. So, but X is positive. So this means you are going to pick only X equal to the radical 2. And so the limit for the X are going to be between 0 and radical 2. So that's going to be your X. Okay, any question? Now, the Y is going to be clear because Y is between 0 and, it's going to be between 0 and Y equal to the X. Even if if you graph it, you will see it. Okay, so the Y is going to be positive and it's going to be less than X. So this is going to be Y. Any question? Even if you graph it, you will see it. So that's it. Now we can set up the integral. So the integral is going to be, we go with the X at the end, 0 to radical 2. In the middle, we go with the Y, which is going to be 0 and X. And then we start with the Z, which is a 0 to 2 minus X squared. And the function is X, Y, Z. Is a rectangular one, so we go with the Z first, dz, dy, dx. Okay, and the integral is something straightforward to find it. Okay, so you do the Z first. So this is going to be 0 to radical 2, 0 to X. If you do the Z first, so that give you 1/2 of the X, Y, Z squared. Z going from 0 to 2 minus X squared. And then we come back and you take the rest. If you put the 0, we get nothing. You can pull out the 1/2. It's going to be 0 to radical 2 and 0 to X. So that gives you XY times 2 minus X squared all squared. Okay, then you go with the dy and the dx. Okay, I just put the Z equal to the 0. So I can integrate respect to the Y easily because the Y is here only. That give me Y squared over 2. All the others are going to be constant. So I don't have to simplify it now. So this would give me 1/2 integral from 0 to radical 2. Then this would be 1/2 of the XY squared. 2 minus X squared all squared. Then Y going from 0 to X. Then I come back and do the dx. Okay, if you put Y equal to 0, you get nothing. If you put Y equal to the X, that give you an X squared here. And the X squared times X would be X cubed. Then you can start working on that, okay? So move out that 1/2 outside, it's going to be 1/4. Okay, it's a 0 to radical 2. So it's going to be just 1/2 X. So you are going to have another X because of the Y, so that we get X squared. Okay, it's going to be X squared, and this would be 2 minus X squared squared. Eventually I have to square it, so I square it now. 4 squared twice after first times second, plus the square of the last part. Okay, so that gave me the dx. Any question? I just moved them around. So X times X squared would be X cubed. So I have another 1/2. I can pull even that one out. So that give me 1/4, and this is what I have to do to integrate the last part. So it's going to be 0 to radical 2. Okay, so that would be an X cubed. and I multiply the x cubed inside, and then I integrate it. So that gave me 4x cubed. 4x cubed minus 4x to the fifth. Okay, and plus x to the 7, x to the 7 dx. Okay, so this can be easily done. Okay, all the powers are odd. When you integrate it are going to be even, then they will take care of the radical 2 for you right away. So nothing to worry about. So it's going to be 1/8 and integral. So that gives you 4x to the fourth over 4. So 4x to the fourth over 4, the first one, minus 4x to the fifth, x to the 6 over 6, and plus x to the 8, x to the 8 over 8, to be evaluated from 0 to radical 2. If you put 0, we get nothing. If you put the radical 2 simplified, do it for yourself, answer would be 1/6. You know, all of them are nice. You see radical x to the fourth, x to the 6, x to the 8. So it can be easily simplified. Okay, so that gives you another experience of how you handle this. Okay, that's number 7. Want to make sure you get enough time to get the other 4. So that was number 7. Any question? Number 8 and 9 are spherical coordinates again, easy format, so we can quickly check them. Okay, so we got enough information, really practice, you know, when we give you a region, it's going to be very similar. And you got the idea how to put it up. Okay, so let's get the 8. We need to get one of those change of variable as well. Okay, this is easy, a spherical one, so get it for a reference. Do it right away. We already talked about it. Just one spherical coordinate. So you've been asked, use a spherical coordinate. Use spherical coordinate to do this one. Spherical coordinates. Again, it's a very symmetric, nice format to evaluate. Okay, to evaluate this integral 1, 2, 3. And that's a G. Again, you know, format is nice. So it's a x squared plus y squared plus a z squared. And the dv, you know, the underlying region is the point inside the sphere, which is very good. So all those smooth one are the one that you did with the sphere. Okay, inside. This is it. Easy to set up. The sphere, quickly get the row. You know, because x squared. The sphere, the center, at the origin with the radius of 1. So the radius of the row. So row between 0, 1, done. Then you have to, okay, then you have to drop it z equal to the 0. Okay, so that would be done, x squared plus y squared. That give you less than equal to 1. So that would be, okay, that would be a circle. So it's going to be a circle, unit circle, data between 0 and 2 pi. There is no restriction on the phi between 0 and pi, easy. And the function is also easy because radical x squared plus y squared, x squared plus y squared, z squared would be rho squared. So that gives e to the rho. You need only something to avoid the integration by parts if you like, which is not possible. So that would be the only challenge that you have, okay? So these type, you may end up with the integral. I gave you one the other day, but this is another one. So that's why we repeat it. So there you are. So we get the G, this is our G, so we check it. So the G is just a point inside the sphere. So this will make it into the rho square less than or equal to 1. Remember, rho is positive number. So rho would be, okay, that's it. The rho would be less than or equal to 1. So you have the restriction for the rho. This is the first part. Projection into the XY plane. Projected unit circle. Projection onto XY plane by letting z equal to the 0. So we end up with x squared plus y squared less than or equal to 1, which is going to be a unit circle. Okay, everything inside this circle. So this quickly means the polar angle is 0 and 2 pi. The inclination angle is 0 and pi. So we have all the limits. Now we go for it. Change it to the polar form. So that's it. At the end, we do the data. In the middle, we do the phi. At the beginning, we do the rho, 0 to 1. Function e to the square root of rho squared. You have to change it, and x squared plus y squared plus z squared is rho squared. Extra term for the polar coordinate, rho squared sine of the phi. Make sure don't miss it. Okay, and then you integrate respect to the rho, integrating respect to the phi, and integrating respect to the data. Okay, now we put this together. So the first step is you have to do that integration by parts. So this would be kind of rho square e to the rho, then the sine of the phi and rho of the phi, d of the phi, d of the data. We did this one the other day. Okay, just use those shortcuts that we talk about it. So I just remind you, just give you the answer is a rho squared e to the rho d rho. That's the first part that you have to find. Okay, use that integration by parts that we talked about what we did the other day. This is going to be the answer. 0 to 1 rho square e to the rho. If you do it so that you give you rho square e to the rho first minus derivative 2 rho e to the rho derivative again. So that gives you negative positive 2 e to the rho from 0 to 1. That would be e minus 2. We did this one before. Okay, you go back, it's a number, you pull it out and start integrating the sign. Okay, so we end up with I equal to e minus 2 out, left over, 0 to 2 pi, 0 to pi. The function sine phi. Sine phi, d phi, d data. So we integrate the sine. Okay, that's it. We integrate the sine. Integral of a sine is going to be negative cosine. That between 0 to pi, that give you 2 again. So it's going to be equal to e minus 2, 0 to 2 pi, negative cosine of phi, but the phi going from 0 to pi. Then we come back and we do the d data. This would be 2. It's a e minus 2 integral from 0 to 2 pi. If you substitute quickly, you will see it, that this is going to be negative cosine of the pi minus negative cosine of the 0. Then the d data. So this is the pi and -1, and this is 1. So that give you negative, negative, positive, negative, negative, positive. So that give you 2. Okay, so all of them would be 2. So we can put it out. It's going to be 2 times e minus 2 integral from 0 to 2 pi d data. So that gives us data. It's going to be 2 times e minus 2 data between 0 and 2 pi. And if you substitute, it's going to be 2 times e minus 2 times 2 pi. So the final answer is 4 pi times e minus 2. So that gives you the final answer. Okay, so that was polar coordinate one. You know, it's unavoidable. You will see this one that you need it. Okay, so this is number 8. Number 9 is a very special problem. If I get time, I'm going to explain it for you, but otherwise, you know, I can post when I post the solution, I put that solution for you. You can check it. It's a very unique problem. It's not difficult, but it takes quite a while to do it. Okay, and I can show you if you like. This is the only one which is different. Let's see how much time do I have. Then I go, yeah, I can do it. So I show you. This is it's a very unique problem among these. It's very similar to this one, but you see, the one that we did over here, those spheres are a nice one. They are nice because the center is the center of the sphere is the origin. But you may have a shifting in the center. You see, if you shift the center to the right, to the left, that in that case, the center is not going to be the center is not going to be the origin. If it's not going to be origin, it can be done, but the situation would be different than the situation for finding this limit of integration. It's not going to be as easy as this. It's not bad to get this experience. It's a very unique problem. If you check any calculus book among the assignments, this is one of them. But it takes time. But I promise you that we are not going to give you that one on the test. It takes time. It's a very, very nice problem. So you must know how to do it. Okay, that's why I'll show you. That's number 9. Let's see, again, you learn something from this. You want to use a spherical coordinate to do this problem. Okay, so, sorry, that's a number, yeah, that's a number 9. And number 9, then we get the 10. Let's see how far I can go. Okay. Yeah, I just show you some part of this. Yeah, at the beginning, it's important. I show you. Then the 9 and the 10. 10 can be done with the, yeah, 10 is a cylindrical coordinate. Okay, let me just explain the 9. You see, the 9 is you want to use a spherical coordinate. Use a spherical coordinates to do this, to evaluate this integral. Integral seems to be nice. You see, 1, 2, 3. And the function is a nice function. X squared plus y squared plus z squared. Okay, and the dv. So if we go to the cylindrical, this is simply what? Inside is rho squared, that gives you rho. But the domain is different. You see where? What is G? G is going to be a collection of points, x, y, z, that satisfy this equation. X squared plus y squared plus z squared. But this is less than equal to x. You see? Is less than equal to the x. So it's not less than equal to 1, 2, 3 that you have it, or the other one. That make it different. You know, a different problem. Okay. So as usual, you have to check your z to see because the function is nice. So this is not going to be a sphere centered at 0. So you have to set it up to see what's the situation they're going to have. Even if you drop it down when you put c equal to the 0, again, you get x squared plus y squared less than or equal to the x. So in that case, again, in the projection is also not going to be a circle centered at 0. So the origin would be shifted. So that's why I make it a little bit more involved for you. So let's work on it. You have to check to see what's going to be the center. So the situation that we're going to have for the solution, this is how we are going to start. We're going to start to get a good feeling of this. So let's to be equal to check it. Okay, you have to move x to the other side. So that give you x squared minus x if you like. And that would be y squared plus z squared equal to the 0. So you have to make a complete square, remember? Because your center is not going to be 0. So to make a complete square, remember, you divide this coefficient by 2. So that gives x minus 1/2 all squared. But minus the square of the 1/2, which is a quarter. Okay, because when you square it, we get x squared. Twice after first time, second, just the x. Then it's going to be a square of a second one, a positive quarter. That's why you put the negative quarter to make it up, okay? And then you have the y squared and the z squared equal to the 0. So if you move a quarter to the other side, you see this is what you are going to have, you see? So again, it's going to be a sphere. It's going to be a sphere, but the center of this sphere is going to be what? So the center of the sphere is going to be 1/2 0 0. And the radius of a sphere in this case is going to be just 1/2. Okay, the radius of this sphere. So the situation is going to be, so you cannot decide so far to see what is going to be the, okay, so the rho is not just ordinary one because you have the shifting here. So what you have to do to see what is going to be the restriction for your rho is you have to go back and substitute for the x, y, z, substitute the spherical coordinates to find out what's going to be the restriction for the rho for this type of sphere. Okay, so this is the way we're going to do it because it's not going to be like the other one. You can use it. So we say, oh, okay, I'm going to try something else. I'm going to try the fact that x, I'm going to substitute. I'm going to substitute the x is going to be, remember, x is a rho cosine of the data sine of the phi. Y is what? Y is a rho sine of the data sine of the phi. And the z is what? A rho cosine of the phi. Substitute in this. Okay, if you substitute, these are going to be all squares. Then you can factor it out. So it's going to be rho squared cosine square of the data. Okay, sine square of the phi. It's going to be plus rho squared sine square of the data and the sine square of the phi. And z is going to be rho squared cosine square of the phi. And the x is simply a rho cosine of the data sine of the phi. You see, that's the situation we're going to have. Now, a little bit of algebra makes things easy for you. You see over here, you can factor out the rho squared, what's that? Sine square of the phi. If you factor out, the leftover is going to be cosine squared plus sine squared, which is 1. So that gives you 1. So you end up with the rho squared sine square of the phi plus the rho squared cosine square of the phi. Phi which is going to be rho cosine of the data or sine of the phi. Okay, and then you factor out again a rho square out, so that give you sine square of the phi plus cosine square of the phi, and that give you rho cosine of the data sine of the phi. Okay, so this is it. This would be 1 again. And you can simplify one rho. Eventually, you get the rho equal to the, okay, rho is equal to the cosine of the data sine of the phi. You see? So you won't get the fact like, the other one that we got. We did from the polar coordinate, the slice of the pizza, etc. So for this shifting, so we get the restriction for the rho. So your rho is going to be between 0 and cosine of the data sine of the phi. So when you're integrating, the part of the rho is going to be, because of that shifting, so that give you the rho. Okay, any question? So that's something extra that you have to know how you handle it. Then you have to get the projection into the XY plane to see what's going to be the polar form. Okay, so what's going to be projection, okay, onto the XY coordinate, XY plane. So the projection means you have to put z equal to 0 in that equation. Okay, so if you put x equal to the 0 in this equation, z equal to the 0 in that equation, so that gives you just a circle. Okay, so you end up with this one, x minus 1/2 all squared plus y squared equal to 1/4. So that gives you the case. It's a circle. It is going to be the circle, okay. It is going to be a circle, but it's not centered at 0. So this is it. It's going to be a full circle. So you have no restriction on the phi. It's going to be between 0 and pi. You have to identify this. You see, the center is going to be 1/2 and 0. So this is going to be 1/2. Okay, this is going to be your center. The 1/2 to the right, 1/2 to the left. So this is going to be 1/2 again. Okay, so this is it, the 1/2 top and 1/2 down. So this is going to be the circle. Okay, this is going to be your circle. So this circle, the radius of this circle is 1/2. The radius is 1/2. I mean, if you think about it, this is going to be 1/2. And this is going to be 1/2. Okay. So this is going to be in a two-dimensional that you have. So in this case, you are interested in the polar. Okay, you are going to be interested into the polar angle only. So this is going to be the polar angle that you are going to say this is it. Remember, the direction is going to be counterclockwise to get this part. So the bottom and the top of this is going to be in these two quadrant, yes. So the data is going to be between -π½ and the π½ This is going to be the polar angle to cover this direction orientation they're going to have here. But your phi is going to be just the usual pi between 0 and pi. So this is make it different from the other one. And then your substitute is just when you substitute, then you'll be able to handle it. Okay, I write it down quickly for you, but it takes quite a while. Let me just quickly substitute and read it for you. You can continue yourself if you would like to get it through, okay? But this part is different, so we just wanted to know it. And now we are ready to, so the rho is going to be between 0 and cosine phi sine phi, and you have the data and you have the phi, so that's it. We can get the function done. Let's see Why I said we are not going to give you this one on the test, because even if you set it up, then it takes quite a while to be able to do it. Okay, but not bad. It's an excellent problem, really. So there you are. What you have, if you remember, this is the integral 1, 2, 3, g. And we have the x squared plus y squared plus z squared. Okay, and the dv. So what we did, we change it into what? I do the data at the end, negative pi half, the polar form first, polar angle. Then I do the phi angle, 0 to pi. Then we start with the rho. Start with the rho. Remember, the rho started from the 0 and going to the cosine of the data, sine of the phi. The function is easy. It's a square root of rho squared. But extra term is rho squared sine of the phi. Okay, rho squared sine of the phi. Then the other part. So I integrate with respect to the rho, integrate with respect to the phi, and is with respect to the data. So this is how you, I'm sorry, this is, yes, that's correct. Everything is correct to get these numbers. Okay, what's the question? Can you explain again how you got the limit of integration for the data? And how you know it's only right side of the circle? It's not the right side of the circle, it's both sides. You see, this is the circle that we have. You see, this is a circle that you have. So you have the, when you go in the polar coordinate, when you have a polar coordinate and you identify each point, you know that each point would be, at each point you have the r and the theta, and your data would be everything that you're going to have. So in this case, you see the center is here. So if you want to characterize it in the direction that we have, if you go around the circle, the bottom one is going to be this, the lower one and the top one. Okay, so if you just pick pick different points, if you pick different points, so you are going to be between the negative pi half and the pi half that you have. You can check these points here, okay, with the coordinate that you have, with the xy coordinate that you have, and find the r and because the r is 1/2. R is 1/2, then the way you're going to get to this point, you will get it at this, which is going to be the pi half, and this is going to be the negative pi half. And that will cover every point or every row that you're going to have. Just check a couple of numbers to check these four. You see, check these four, 1, 2, 3, 4. You arrive at that negative pi half and the pi half that you're going to have. Okay, very good. So let me just put these to see what would be the next difficulty then. So let's go back. This is rho. So that would be rho cubed negative pi half. It's a very nice problem, but you've got to be very patient to be able to get it right through the end. So it's a 0 cosine of the data sine of the phi. So this is going to be rho cubed sine of the phi. Okay, d rho d phi d data. Okay, now if you do the rho, good luck. You see that give you rho to the fourth when you integrate it. So that gives you rho to the fourth, okay? Then because that's your rho cube, rho to the fourth, and then you have to substitute here. So it's a negative pi half, 0 to pi. So I got a quarter. Okay, I got a quarter of rho to the fourth. Then I have the sine of the phi, okay. So I have to check my row from 0 to the cosine of the data, sine of the phi. You see, that's going to be the one. Then we get the d row, d data. But if you substitute, I can pull out the quarter. So that give me negative pi half to the pi half. Okay. And if you substitute, you get this one. It's going to be 0 to pi. If you substitute the top one, that give you cosine to the fourth of the data, sine to the fourth of the phi. Then you have the sine of the phi extra. Then you want to integrate respect to the sine of the phi and the data. So that gives sine to the fifth. So negative pi half and the pi half, 0 to pi. Cosine to the fourth of the data, sine to the fifth of the phi, then the d phi, d data. You see, that's a challenge for the other steps. Is going to be when you want to integrate respect to the phi, you have to integrate sine to the fifth. Good luck, you know that. The odd power of the sine, you have to break it into sine to the fourth and the sine, and then you start integrating to get this one through. Okay, so if you like, you do it for yourself. I put the complete solution of this one when I give you my note. Okay, so you have to find this one first. You see, that's going to be your first challenge. If you want to do it, you have to do it by integration. By breaking it, you know that you break into the sign. You pull out one sign and then you change everything else to the cosine. Then u prime give you this number. So when I post the solution, I give you the complete solution of this, but this would be 16 over 15. But even if you do this one, you see the next challenge is going to be when you substitute, you get cosine to the fourth. That would be another challenge. You see your phi is going to be a quarter, integral from negative pi half to the pi half. Then you substitute this number, that's going to be 16 over 15. Then you have to find the cosine to the fourth of the data, d data. Every solid problem from calculus 2, it comes here. So you simplify these two, that give you 4. So if you pull it out, that gives 4 over 15, integral from negative pi half to the pi half. You can use your calculator to find these integrals. You see, you know that cosine, even power of a cosine. You have to write it down in the form of the double angle. You see cosine square is square, and then you do it. So you have to find the way you do it, just for your information, is cosine to the fourth. We write it down as a cosine squared, then squared, and then we use the double angle formula. Cosine of the 2 data over 2 all squared. It takes times, but it can be done. And so if you do this one, eventually you can find it and just get them together. The final answer is going to be, you can find this one by your calculator, but this is the final answer, pi 20. So as I told you, it's a great problem. It's different from any other that you will see in calculus 3, but it takes times. But we wanted to know it. Of course, we are not going to give you on the test. Okay, so this is going to be the number. Okay, this is going to be number 9. Number 10 is similar to this one, but it's a cylindrical coordinate. So I would like to give you one of those change of variable, but I post a solution of 10 for you. So I guarantee that I'm not going to give you this one, but I don't guarantee that I'm not going to. I may give you the next one. This next one is, again, it's a very popular problem. So you better check that the solution is not bad, because we did this one for you before, a similar one. So you want to find the, remember, you want to use cylindrical. I just write it down, but I give you the solution. Okay, so you have to So you want to use cylindrical coordinate. It's not bad. These two problems in calculus 3 are, are the VIPs really of the triple integrals. You don't have anything as deep as these two problems. You want to use the cylindrical coordinates to evaluate this integral. 1, 2, 3. It's a y squared z, and you have the dx, and you have the dy, and you have the dc. Okay, but we did this one somehow, but your G is going to be a solid. Remember, I think we did this one. It's a solid that's bonded. You see where G is a solid. G is going to be a solid bonded between, okay, yes, we did this one. G is a solid that's bonded. Okay, that's going to be bonded above by a sphere. Okay, by a sphere of x squared plus y squared plus z squared equal to 4, and below by the core z equal to the, yes, I did this one, but I will post the solution. I think the one that I did, the radius was different, but everything else was the same. Okay, it's not difficult with the cylindrical one. This one quickly can be, that the only point is, yeah, I did this one. I emphasize that the z part is the one that the people are going to be in trouble. Okay, I talk about it that you have to intersect it to get the since you want to do it with the, you see your z. I just explain this part again, because to get the z part, this is x squared plus y squared plus z squared equal to the 4, and this is going to be z equal to the x squared plus y squared. Since it's going to be a cylindrical form, so your z is going to be fixed, but you have to change them into the, change them into the polar format, if you like. So the way we do it, the first one is just r squared plus z squared equal to 4. So that gives you z equal to positive negative 4 minus r squared. And the second one is easy, because the second one would be simply radical r squared, which is equal to the r. So the restriction for the z would be just between r and a square root of 4 minus r squared. So it's no problem. But the one that the people they miss, I talk about it, is when they drop it down. Projection onto XY plane. The way they do it on the test, they replace this z by 0, and they claim that they have x squared plus y squared to the 4, and they do the polar form, which is not correct. You have to find the intersection of these two. Okay, I talked about it the other day. So you have to find the intersection to get these numbers done. Okay, so the intersection means you substitute for the z, so that gives x squared plus y squared plus radical x squared plus y squared all squared equal to 4. So this would be x squared plus y squared, and the x squared plus y squared equal to 4. So that gives you 2x squared, 2y squared equal to 4. So that gives you x squared plus y squared equal to 2. So the radius of your angle is a radical 2, is not 2. Okay, so this means You see this is going to be the case. So it's the radical 2 and the radical 2 that you have. Okay, so that gives you the restriction for the R, the radius, a radical 2. Okay, and the polar angle is between 0 and 2 pi. So just make sure that when we get these two z's, then get the correct one. It's not 2. And the rest are going to be easy. I did it, and just check it for yourself that you just substitute. I just substitute in case you don't have it. So there is going to be 0 to 2 pi. R is 0 and radical 2. Z, as we talk about it, is going to be between the bottom one is R. The top one is radical 4 minus R squared. And you just substitute for this y squared z. You have to substitute for the y squared. Y squared is R cosine of the data. I'm sorry, y sine. R sine of the data, all squared. You keep the z, an extra number. The extra number is R. Then it's a dz, dr, d data. Okay, so be careful. The one that we did, maybe the function was different. But the rest are going to be now nicely done. And I'll post the rest of the solution for you. But if you do it, you get 2 pi third, the final answer. Okay, so pay attention to the 9 and the 10. Make sure you understand these methods, which are a little bit different from whatever we did. Okay, whatever we did before. So what's question? Okay, that's it. So there are two about those change of variable. I put the solution for you because it's very similar to the one that I did the other day. Okay, remember the first one was e to the x plus y over y minus x. Okay, so that's it. So I do this recording and I post the solution for you quickly. Then as I talk about it, it's going to be 10 questions and you answer 9. I grade that quiz and post the solution for you. Remember, you have to study that quiz. The quiz, practice the one, and keep everything for the final. That's it. Have a good one. Let me know if you need anything. Bye-bye. Thank you. Bye-bye. Thank you. Thank you.